Hey guys, sorry I couldn't make it today. Some unforeseen circumstances prevented me from coming to work today, but I'm here nonetheless. So I'll be back tomorrow. No worries. But yeah, let's get to learning some calculus. So last time we started learning the basic rules of differentiation, namely the power rule and how you can add and subtract functions and use, when you add and subtract functions and you differentiate them, you can take the derivative of each one of those pieces, right? And so we found out that basically polynomials are really easy to derive. So today we're gonna basically go off of that idea, and we're gonna show some applications of these derivatives. Namely, we're going to be using the power rule to show that instead of having to do the definition of a derivative like we normally have been, we can just use the power rule and get straight to things like instantaneous rate of change, instantaneous velocity, without having to use those formal definitions of a derivative. So yeah, let's get started. All right, so let's start out with the first part of our notes. The example asks us to sketch the graph of a function f such that f prime of x is less than 0, and for all x, and the rate of change of the function is increasing. So essentially what it's asking us to do is graph a function whose slope is negative, right? That's what f prime less than 0 means. But the rate of change of the function is increasing. So that means that we have a negative slope, but that slope is increasing. Okay, so we're going to draw ourselves an XY graph, right? Here we go. So let's draw ourselves an XY graph. Okay, and so what we're looking at is we want to graph a function f, right, such that f prime is 0. So a function that would have a slope of 0 could look one of two ways. It could look like something like this, or it could look something like this, right? So in either of these cases, our slopes will be negative, right? Now the question is, which one of these two graphs has a slope that is increasing? In other words, which of these is increasing in value? So if we look at the tangents, right, compare that point compared to the tangent at this point. We look at the other graph, compare the tangent at that point and compare it at this point. Okay, which one of those slopes has gotten larger, right? So if you look at these two, larger meaning more positive, right? It's pretty easy to tell that this function here has a slope that's increasing, right? It was very negative up here, but then it starts getting less negative. In other words, it's becoming more positive. Over here we have something that's slightly negative, but it gets increasingly negative. Okay, so if we have something that's supposed to be a slope less than 0, so in other words a negative slope, however the rate of change is increasing, in other words the slope is getting more positive, we definitely want to graph something like this. Okay, so our f of x function, so this would be f of x, okay, our f of x function is actually going to look something like that. Okay, and it could go on and do something different, right? It could go up, it could go down, or whatever. But for this point, we have a function of f, okay, f of x, and all of its slopes are very negative, but they get less and less and less and less and less negative. Okay, to the point that this is indicating to us that f prime of x is actually increasing. So yes, it is less than 0, but it is increasing in it is a rate of change that is increasing. Okay, so let's move on to the next one. It says find a and b so that f is differentiable everywhere, and they give us a function f of x, and it's a piecewise, and they've defined it such that for every value less than or equal to 2, we're going to use ax squared plus 1. And for every value greater than 2, we're going to be using b times x minus 3. Okay? So the question is, we want to choose an a and a b so that f is differentiable everywhere. Okay, so this is what our f of x is. So that means that if this function is going to be differentiable, particularly at this point x equal 2, then what we need to ensure is that this piecewise is continuous there, right? So that will establish some a's and b's for us to kind of work with, right? So remember, the definition of differentiability, we have to have a function that's continuous, right? No sharp turns, no gaps or anything. But the big thing is that if a function is continuous, then it's differentiable, right? So, or I should say, if a function is differentiable, it must be continuous. So let's start out with that. Okay, so we know that this function has to be continuous at the point x equal 2. So we're going to have to take the limit. Okay, make sure the paper is lined up. The limit as x approaches 2 from the left, so that'll be the first one, right? Anything less than 2, of ax squared plus 1 is equal to the limit. This has to be equal to the limit as x approaches 2 from the right, okay, of bx minus 3, because that's the function that we're using to the right of the of 2, anything greater than 2. So now we want to evaluate. Okay, so let's see, if we plug in 2 into here, we get 4ax, not 4ax, just 4a plus 1 equals, if we plug in 2 here, we get 2b minus 3. All right, so at this point we could probably use this or some form of this later on, right? I'm gonna leave it right here though, because one way might be a little bit easier than another to solve later on. Okay, so let's go on to the next part of this. The next part is, if this is differentiable at 2, then that means that the tangent at that point has to be equal on both sides, right? In other words, the slope of that tangent has to be equal on both sides. So what we also need to prove is that the tangents of both of these are equal. So in other words, we need to come up with what the equation is for f prime. So if we solve for that, we find that f prime of x as a piecewise, okay, is going to be equal to, well, if we derive this using the power rule, it becomes 2ax. The 1 goes away because it's a constant for every x value less than or equal to 2. Okay. Then when we derive the next one, we get that the derivative, or the slope of the tangent, has to be b, because it's x to the 1. You use the power rule, it becomes x to the 0, minus 3. This 3 is a constant, so it's just going to go away. In other words, this function will simply be b for every x value greater than 2. Okay. So then what we have to establish is that these two are equal to each other, right? So at 2. So what we're going to do is we're going to essentially evaluate the limit, right, at 2, because what we're saying is that if the tangent is the same, then the limit of the derivative function as x approaches 2 must be equal on either side, right, as you approach from the left and from the right. So in other words, we're also going to look at the limit as x approaches 2 from the left of 2ax, and that has to be equal to the limit as you approach from the right of b. Okay. Now if we evaluate this one, plug in 2, we're going to get 4a is equal to simply b. B is just a constant in this case. Okay, so there's nothing to plug in 2 or plug 2 into, and so we just end up with b. So what we end up with here is that b is equal to 4a. So if we're going to solve for an a or a b value, it's going to pretty much be easy to plug this guy into here, right, and then solve for a. So that's what we're going to do. So we're going to take this value, this equation, and we're going to solve for our a value. Okay, give me a second. There's a bit of a noise. All right. So we're gonna plug in here. Okay, so we plug in b. So b is going to be equal to 4a. So we're going to keep this side. 4a plus 1 equals 2 times, if b is 4a, we substitute that in place, minus 3. Now we have everything in terms of a, right? So multiply things out, move some things over. So I'm going to move this 1 over. So we're going to subtract 1. Okay, actually, it might be best to add 3 now that I look at it. Alright, we're going to add 3 because we're going to have more a's on this side than we will on this side, so it's going to be better for us to keep the a's over here. So that'll give us 8a equals 4a plus 4. Move the a over so that we end up with 4a equals 4. Okay, so we're here, so that implies that a must be equal to 1. So now we know what a is. We can go back here, okay, and plug in what our a value is. So 4 times 1 is 4, so that means that b must be equal to 4. Okay, so what we end up with is a function f of x, which is equal to this piecewise of a is 1, so just x squared plus 1 for every x value less than or equal to 2. And then we have a b value of 4, so that means it'll be equal to 4x minus 3 for every x value greater than or equal to, or not greater than or equal to, but just greater than 2. Okay, so I'm going to take a second and I'm going to plug this into the calculator just so that we can see that this does in fact match up nicely. Okay, so let's see if we can get this to focus a little bit better. All right, so here we have our calculator. We're going to go to our y equals. Okay, so that would be diamond F1 if you're using the TI-89. So we're going to type in x squared plus 1, all right, for our first one. And then for our second function, we're going to type in 4x minus 3. Now, the really cool thing about the TI-89s is that you can specify domains. And the way we're going to do that, we're going to say it's going to be x squared plus 1. And we're going to use the little bar, okay, next to the 7. And what this bar is basically telling the calculator is such that, okay, so it's establishing the domain. So we're going to say that this is going to be x squared plus 1 such that, or for only values of x which are less than or equal to 2. Now a neat little trick here is that you have your less than symbol here, right, for second 0, but if you hit diamond 0, okay, let's show you that, diamond 0, it actually gives you a less than or equal to, okay, so less than or equal to 2. I hit. So now we're going to change the domain for this one. So we're going to say that we're going to graph this for every x value greater than 2. So greater than is the decimal. So second decimal will give us greater than, and then we're going to say 2. And so now when we graph this, let's see what it's going to graph. Okay, so it's going to graph up until 2, the first function, and then it's going to continue graphing the second function. And what you can kind of see is that there's a teeny little break right here, okay, and that's essentially where you have your less than or equal to and your greater than. So the greater than is kind of like that little hole that's there, right, but it's technically filled in completely, okay, by the x less than or equal to 2. Okay, now if you zoom out, let's see, how do we zoom on this guy? It's been a while. Zoom, right, F2. So let's zoom out. So we're going to zoom out. We're just going to hit from the center, okay, and it's going to graph it, right, and so you can see that 2 is much shorter there, and then this is going to be your 4x minus 3, okay, and so what you can see here is that your slopes are definitely the same, right? If we zoom in on, let's see, let's zoom in. Let's do a zoom box, okay? And I'm going to zoom from here to there, okay? And we're going to try and capture what's happening here, okay? So you can see, right, that there was a gap there, but then it picked up again, right? So let's zoom back out to the standard window, and what I want you to see is when we zoom in really close at that point 2, that it's gonna get flatter and flatter and flatter and flatter, right? So let's see if we can do a zoom in, but what we're going to actually, what might be easier, trace and go to 2, right? Can we just plug in 2? Yeah, there we go. If you type 2 on the calculator, it'll put you exactly where you want. Okay, so there we can see underneath the cursor there's a gap, right, because of this greater than 2. So if we zoom in now at that point, okay, there's a stop. That's where the left part stops, and then that's where the right part picks up. So we still have that little gap. So let's zoom even further. Is it working? No, it's not working. Okay, so let's zoom in further. All right, so we're gonna zoom in even more. Okay, and you can still see kind of a bit of a curve here from the x squared piece, right? So let's trace one more time. That's not what that is, right? We're gonna trace at 2. Okay, so we're gonna do F2 to zoom, and then we're gonna do 2 to zoom in, and we're gonna zoom in there yet again. And what you notice is as we start zooming in more and more and more and more, what you start seeing is that this line is getting straighter and straighter, right? Or this curve, this x squared, is getting straighter and straighter. So this is the concept of local linearity, right? And we mentioned this before when we were talking about functions that can be differentiable and functions that are not differentiable. is that, or sorry, not differentiable, continuous. We said that functions can be continuous on a certain interval, right, as long as it shows local linearity. And what we're seeing here is that local linearity, okay? The fact that if you were to zoom in really close in on that point, right, that this is essentially a straight line, okay? So locally speaking, this curve, this x squared, is just as straight as the 4x minus 3, okay? So clearly here we can see that with the values of 1 and 4 that we found for our a's and b's, that we end up getting a perfectly connected line, and we end up having a slope of 2 exactly at that point, right? Or is it 2? Is that what we're looking for? I don't think it's a slope of 2. It's a slope of 4, right? It'll be a slope of 4 at that point and a slope of 4 at that point for x squared, okay? So let's kind of look at the table real quick and see if we can see anything, right? So at 2, it's okay. So what this is showing you, right, is that the function 4x minus 3 is undefined until you get to 2, or I should say something like 2.00001, and then it's defined. Actually, that wouldn't be a bad thing to see, right? So if we go to F2 setup, we go to make an independent variable ask, and then save. I think we can delete these, right? Okay, so we're gonna plug in something like let's plug in something like 1.9, 1.999, and then 1.9999. Okay, so I wasn't paying attention. 1.99, okay, 1.999, and then if we go from the other side, 2.001, okay, 2.01, 2.1, okay, you can definitely see here, right, where x squared leaves off, your 4x minus 3 picks up, okay? So if we were to plug in 2 in here, right, it's closer and closer to 5, but then because the 4x minus 3 can't equal 2, right, we end up with an undefined value for a 4x minus 3, but right after that we do have a defined value, okay? So that's how we solve those problems. All right, so that's that. Let's move on to the next one. And guys, I know that it's hard because if you do have questions and I do need to give you feedback, it's kind of impossible right now because we're in video mode or whatever. But I assure you, if you do have any questions over any of this, we can go over it again in class the next day, okay? So let's do this next problem. The next problem says, at time t equals 0, a diver jumps from a diving board that is 32 feet above the water with an initial velocity of 16 feet per second. Use the position function s of t equal to negative 16t squared plus v naught t plus s naught, where v naught is the initial velocity and s naught is the initial position. For those of you that aren't familiar with what I'm saying, naught is basically 0 in British English, right? And so instead of confusing everyone by saying v sub 0 or s sub 0, okay, because when I start talking faster and I say v sub 0 or s sub 0, it sounds like I'm saying something else like s of 0. So if I say v naught and s naught, it's pretty much clear cut what it is I'm saying, okay? And naughts are usually your initial values for whatever it is you're talking about. So in this case, v naught is initial velocity, s naught is initial position, okay? All right, so they give us a function s of t. It says, when does the diver hit the water? So we're trying to figure out when the diver hits the water. Now, what they've also given us is they've given us 32 feet above. So that's our initial position right here. and they've given us 16 feet per second, which is our initial velocity. But that's not quite right, because if you're jumping off a diving board, you're going down, right? Which means that your initial velocity is going forward and down, right? So technically speaking, this velocity should be negative, right? Because if you think about what the curve is doing, your slope of your tangent is going to go negative from 0, assuming that he starts here and just starts going down, right? And not that he jumps up and then down. He's going to go straight down, and so we're going to start at the slope of 0 and then just go negative. Okay, so that means that our velocity should be a negative 16 feet per second. Okay, jumps from a diving board 32 feet above the water with an initial velocity. Right. Okay, so it says, let's use this position function. When does the diver hit the water? So that means we're looking for the root, right? Because if this is a parabolic function, that means that we're going to have a root at the bottom. So what we're looking at right now, okay, what we're looking at right now is something where the diver is up here at 32 feet and then dives down. Okay, so this is going to be your position graph. Okay, now what we're looking for in part A is that root of that function. Okay, so when we plug this in, your negative s, your s of t, let me push this up, your s of t is equal to negative 16t squared minus 16 t, sorry about that, that should be a t, plus s naught, which is 32, and this is positive 32 because we're starting above here. Okay, we're starting above the water on the platform. Okay, so let's see, we're going to basically solve for our zeros, right? So first thing we can probably do is factor out a negative 16. So if we're going to do this by hand, right, we're going to factor out a negative 16, which leaves us with t squared plus t plus 2, right? So oh no, not plus 2, we're going to have a negative 2. Okay, so we're going to have a negative 2 because we factored out a negative 16. So we end up two factors that add up to 1 multiplied to 2, so that'll be positive 2 and negative 1, or minus 1, right? So this is negative 16 times t plus 2 times t minus 1, okay? So that's what s of t is once we factored it out. Now, what we're looking for is when this is equal to 0. So what we're looking at is t plus 2 equal to 0 and t minus 1 equal to 0, right? So this one will give us t equals negative 2, and this one will give us t equals positive 1. So clearly we can't use time equal negative 2 because that would be going backwards in time, right? So that means that at time t equal 1 is when it happens. Okay, so in other words, this is going to happen at 1 second after he jumps off the diving board. Okay, so this guy's going pretty fast, right? So we can't use this one, we said, because that's negative. Okay, so we're only going to use time t equal 1. So it says, when does the diver hit the water? Well, at 1 second. Okay. The next part says, find the instantaneous velocity when t is equal to 1 second. So instantaneous velocity, anything instantaneous we know to be the slope of the tangent line at t equal 1. Okay, so if we're going to find the slope of this function, that means that we're going to need, or the slope of the tangent line of this function, that means we're going to need to find out what s prime is. Okay, so s prime of t is going to be power rule drop the 2, negative 32, that's supposed to be a 2, negative 32t plus v naught, right? Because your t will go away, t to the 0 is just 1, plus s naught. S naught literally goes away, becomes 0, okay, because it's a constant. So in other words, s prime of t is equal to negative 32t minus 16, right? Because our v naught was negative 16. Okay. Then if you really wanted to, which will probably make things look a little nicer, let's factor out a negative 16 just for funsies. So negative 16, what are we left with? We're left with a 2t plus 1, okay? 2t plus 1. So then the question is, what's the instantaneous velocity at time t equal 1? So then what we're looking for is s prime of t when t is equal to 1. Or sorry, yeah, when t is equal to 1. So what we're looking for is s prime of 1. So negative 16 times 2 times 1 plus 1. So that's 2, 3 times negative 16 is negative 48 meters per second. Or not meters per second. This one is done in feet per second. Okay. Just look back up here. This one's done in feet per second. All right. And that makes a lot of sense, right? Because when we think about what the diver is going to be doing at this point, what that instantaneous velocity is going to be at 1, the slope of that tangent, it should be pretty steep. It should be pretty negative, okay? It wouldn't make sense for it to be positive, right? So if his velocity had been positive, that would mean that he was literally flying, right? Not diving into the pool. Okay, so we get negative 48 feet per second. So since we found velocity by finding the derivative of position, what that tells us is that the derivative of position is actually the velocity, okay? So the derivative of position is velocity, okay? Then it tells us the last step to find the average velocity on the interval 1 to 2, okay? Now, average velocity is just average rate of change. Average rate of change on A to B is f of B minus f of A over B minus A. So let's kind of look at what the average velocity as they were falling down, or diving down into the pool was. So if we're looking at 1 to 2, okay, then that means that we're looking at s of 2 minus s of 1 over 2 minus 1, okay? So not s prime, just s. So let's go ahead and solve this. If we look at the interval 1 to 2, well, that means we're going to need to solve for what s of 2 is, right? So it might be best to use the factored form. S of t is equal to negative 16 times t plus 2 times t minus 1, okay? And if we look for what s of 2 is, that would be negative 16 2 plus 2 times 2 minus 1. So that would be 4 times 1 times 16. So that's negative 48. Is that right? No, not negative 48, negative 64. Negative 64. Okay. And this would be in feet, right? So it's at negative 64 feet at time t equals 2. So that's a really deep pool. If we look at what the value at 1 is, well, we know that at 1 it should be at 0 from what we calculated, right? So at 1 we should be at 0. So we know then that s of 1 is equal to 0 because that was one of the roots, okay? So if we plug those values in, negative 64 minus 0 over 2 minus 1, that would give us negative 64 over 1, and that would be feet per second. Okay, negative 64 feet per second. So basically our diver ignores the fact that he's in water and just keeps diving straight through as if there was no water, and ends up going really, really fast into the pool. Like I said, hopefully it's a deep enough pool that he survived that. Otherwise, our diver is in trouble. Okay, so hopefully this made sense. Hopefully I didn't confuse you too much with the pondering and thinking that I did while trying to solve this. Okay, and then we have one last part at the end. Okay, and so now we're going to look at this graphically. So we kind of looked at it graphically at the very beginning. So now we're actually given a position function. Okay, it says the graph of a position function is shown. Sketch the velocity function on 0 to 9. So we got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That's all they've graphed here, from 0 to 9. Okay. So the question is, graph the velocity function from 0 to 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's 9. Now, some points that are going to be specifically important are going to be where these points are. Okay, so particularly at 1, 2, 3, 4. Okay, and 5, 6, 7. All right. So we're going to need to label 4 and 7. 1, 2, 3, 4. And then 5, 6, 7. Okay. And why are these points so important? Well, they're important because that's kind of where our slopes change, right? So what's the slope along this line? Well, if we look at the slope along this point, if you don't see it between these 2 points, okay, just use these 2 points. So here's 4. And here's 7. We know that we're at a height of 1, 2, 3, 4, 5, 6 right here, and a height of 7 right above it. Okay, so if we do slope, rise is 6 over run, which is 4. So 6 over 4 will be a value of 3 over 2. So our slope here is 3 over 2. Okay. And we'll call this slope 1. Now our slope along this point from 4 to 7, the slope of that tangent line is going to be the same as the slope of this line, which is a slope of 0. Okay, so slope number 2 is 0. So this is where some of the confusion can come into play, because so far you've known that tangent lines technically only touch one point, right? But the rules kind of break down when you're talking about linear functions, because they are already lines. So any function that is tangent to a line is going to essentially be parallel to that line, or in other words, lie on top of that line. So it's almost like a tangent line either touches just one point if it's of degree 2 or greater, or every point along that line, implying that it's parallel to the line that it's tangent to, right? So in this case, you can see that here, if we were to draw a tangent line along this curve, it would literally lie on top of this curve and would have the same exact slope as this line here. Okay, so in other words, our slope of our tangent is going to be 3 over 2, as the slope of this line is 3 over 2. Much how the slope of our tangent from these 2 points is going to be a slope of 0, because the slope of this line here is 0. Okay, and then the last one, they give us a slope of 1 over 2, right? So slope 3 is going to be 1/2. Okay. So from 7 to 9, we're going to have a slope of 1/2. So let's think about it. This slope never changes. It's constantly 3/2 from here to here. It's constantly 0 from here to here. And it's constantly 1/2 from 7 to 9. Okay. So then what we need to do is we need to make our graph representative of the slopes we have. Okay. So I'm going to say, since we have 1/2 or 3/2 and 1/2 and then 0, okay, let's go ahead and make every 2 a 1/2. So we'll say that 1/2 is right here, and that this is 1, and that this here is 3/2. Okay, just so we can kind of see it better. So then our slope from 0 to 4 is going to be 3/2. So that means that from here to here, 1, 2, 3, 4, right? We have a slope of 3/2, and it's constant. Okay. The slope from 4 to 7 we said was 0. So from 4 to 7 we have a slope of 0 down here. Okay. And then the slope from 7 to 9 is going to be a slope of 1/2. So from 7 to 9, it's going to be this. Well, that's kind of weird, right? All these slopes are basically like, they have jump discontinuities between them, whereas the original slope was continuous, right? There are no breaks here. They're completely continuous. So what we're trying to show you here is that even though this is continuous, it's clearly not differentiable at those points because you have a jump discontinuity, right? Also, looking at what f of x looks like, we have a sharp turn there. So that's why this function would not be differentiable at 4. It's differentiable between 0 and 4 because it shows local linearity, right? However, at 4 itself, even though it is continuous, it's not differentiable at 4 because the derivative from the left is going to be 3/2 and the derivative from the right is going to be 0. Same thing happens at 7. Okay, derivative from the left is 0, derivative from the right is 1/2. And even though it is continuous, it's not differentiable. So what we need to take from this is that differentiability implies continuity. Okay, so if a function is differentiable, it's definitely continuous. However, if a function is continuous, it's not necessarily differentiable at those points. Okay, so that's all I've got for you. If you have any questions, make sure you star them, write them down in this space that you have down here if you printed out the notes. If you didn't print out the notes, write them down on a sticky note or something and save them for me for tomorrow when I get to class, okay? And you can come and ask me in the morning, or you can ask me after school, or you can ask me during class at the very beginning of class before we get started on the next lesson. Okay, so thanks for watching, guys. Hope you have a great day, and I'll see you tomorrow.